Let's look at this curve, for example. You can use some nonlinear equation. Actually, you have more than one choice here. Supposing you select one equation to describe this curve, and it describes a nonlinear curve with a linear response of photosynthesis to light, and then the response saturates at high light. So that's a general equation. And your variable here is the independent variable is light. Light is driving photosynthesis. So that's a variable. The production is the response. So that's a dependent variable. The parameters here are those quantities that determine a specific curve out of a family of curves. That's one way to think about it. For example, if I change alpha, which is called the initial slope, the steepness of this curve near the origin will change. And if I change the other parameter P and B, the maximum value that this curve will generate will change. So the maximum value will go up and down if I change P and B. And alpha, if I change, that will change the slope here. So parameters are what you used to pick out one specific curve out of a family of curves. So when you are doing a model, it is always good to think about which are your variables that you can measure, as was pointed out, and which are the parameters that you have assigned to your model. Very often your model performance will depend not just on the model itself, but also on how you drive the model by assigning parameters. So when you are thinking about choosing a model of primary production to use in your work, think about how well you know or can prescribe the parameters that you want to use in your model. I'll come back to that. So Trevor mentioned here that photosynthetic response is wavelength dependent because absorption by light is absorption by phytoplankton of available light depends on wavelength, and therefore the photosynthetic use that the light is put to is also wavelength dependent. So if you want to do a spectral model, or for that matter a non-spectral model, you need to know how much light is available at depth and how that light is distributed with wavelength. So interestingly enough, the diffuse attenuation coefficient of light, which Trevor introduced, that determines the rate at which surface light is attenuated as a function of depth, is an attenuation coefficient K. It can be calculated using the same optical properties that we were discussing yesterday in the context of calculating ocean color. So whereas ocean color deals with light that's leaving the ocean, attenuation coefficient deals with light that is going down, and it depends on the same properties, absorption and backscattering, which you can split into its components: absorption by pure seawater, absorption by phytoplankton, yellow substance, and so on. Or if you prefer, colored dissolved organic matter and detritus, and anything else that might be in the water, such as suspended sediments and so on. So you consider their absorption and scattering properties, and you can calculate the diffuse attenuation coefficient as a function of these quantities. And because these have spectral dependencies, as we saw quite briefly yesterday, the spectral quality of the light also changes with depth, and it changes with how much of phytoplankton and other substances might be present in the water. If the water is very clear, the spectral form of the light at the photic depth or the 1% light level will be very blue. It's dictated by the water's own optical properties. But as you add more and more absorbing pigments into the water, the light available shifts from blue towards the green. And this has some relevance for photosynthesis because, as you must know by now, for phytoplankton absorption has a maximum in the blue part of the spectrum, typically. And there is a secondary maximum in the red part of the spectrum, but that's less important for the story because most of the red light is absorbed by pure water itself and very high in the water column. But it matters to phytoplankton whether the light available is blue and therefore easily absorbed, or green, in which case they are less equipped to absorb that light. So one interesting thing you can do is to calculate light absorbed by phytoplankton, say at the 1% light level, and see how these the fractional absorption by phytoplankton might vary if you change the type of phytoplankton present and their absorption spectra. And in one of the exercises that we did back some years ago now, what you see is that in the very oligotrophic blue waters, small cells such as Prochlorococcus and chlorophytes do relatively well in absorbing. But as you go towards more eutrophic waters, diatoms do relatively better. Relatively. They all absorb less efficiently in eutrophic waters, but diatoms do relatively better. So it's a possibility that the spectral correspondence between available light and the absorption spectra might have an influence on which type of phytoplankton might thrive in which colored water. If you want to account for effects such as this, there is no way around it but to deal with a spectral model. So in the literature, it can be very confusing. People talk about spectral models, non-spectral models, and this, that, and the other. But if you want to be really sure that you are dealing with a spectral model, look for this. Check that the coupling between light and the action spectrum takes place at the spectral level or not. If this coupling is spectral, then you have a spectral model. If it doesn't have that, you don't have a truly spectral model. Sometimes you see people calculate available light with all spectral detail, but then do the coupling like this without spectral resolution. If you do that, it's not a completely spectral model. That's one way to distinguish really whether a model is spectral or non-spectral. Okay, so the other thing you have to consider is whether your model will be vertically homogeneous or you assign some structure to the chlorophyll as a function of depth. So in our work, very often we use a Gaussian shape to describe a deep chlorophyll maximum, in which case you introduce now more parameters into your model. You need some parameters to describe this chlorophyll maximum, and the parameters of your profile model could be the depth at which you have a maximum, the Zm, the area under the curve, which would be this little h, and sigma, which describes the width of the peak, and some measure of the background biomass over which the peak is superimposed. Some people also introduce a slope to the background. But if you're dealing with primary production, the important thing is to make sure you get things right closer to the surface where the light is. Now, if you are doing or trying to do primary production estimation from satellites, we have a problem. The satellite is not monitoring the entire water column. It is monitoring the surface. And it is not just the surface, it is a finite layer of the surface. And how finite? It's difficult to answer, because once again, the depth over which the satellite signal comes is determined by the optical properties of the water and the optical properties of the water at the wavelength at which satellite is looking at the ocean. But typically, one can say that if at any given wavelength, if there is a certain amount of light reaching the sea surface, it is getting attenuated according to the diffuse attenuation coefficient as it travels into the water column. And again, by another attenuation coefficient, slightly different from that for the downward light, as the light is backscattered and travels back to the surface of the ocean. So it's a double exponential now. It gets decreased exponentially going down and exponentially going back. Therefore, the maximum signal comes from the surface with an exponentially decreasing contribution from deeper layers. And a rule of thumb is that if you know the attenuation coefficient k at the wavelength of interest, then about 90% of the signal comes from the first optical depth in which the light is attenuated by a factor 1 over k. Okay. So satellite is only saying the surface, and you are interested in water column production, and you know that there is a deep chlorophyll maximum that the satellite is not seeing, then we have no way around it but to use whatever auxiliary information we have to supply that information to complete what the satellite may be able to tell you. So the protocol for computing primary production from satellites, or for that matter by any other means, might look something like this. You need at least the light reaching the Earth, but outside, at the top of the atmosphere. Then, if that is all you have, then you need an atmospheric transmission model to compute the light at the sea surface. These days, you can get light at the sea surface in the photosynthetic domain or the photosynthetically active range, also as a satellite product. NASA, if you go to their Ocean Color website, you'll find a PAR product that tells you the total irradiance at the sea surface. Now, ESA is working out a method by which it can be provided in a spectrally resolved form. Anyway, one way or another, if you have light at the sea surface, then you need a light penetration model, which basically means that you have to assign a value of k. And if it is a spectral model, you need spectral k to compute light at any given depth. To do this light penetration calculation, you will need the profile parameters if you want to assign a deep chlorophyll maximum. And if you are in a remote sensing context, you will have the surface biomass from satellites. Then you need some combining of in situ and satellite observations to define the chlorophyll profile values at each depth. So if you know the biomass and the light at any given depth, this is where now you have to assign your model parameters. You have to decide how can I best prescribe for that pixel at that location on that day the value of the initial slope and the saturation parameter. If you have taken care of all those steps, then it is a relatively trivial thing. You compute the primary production at that depth, at that time, at that location. Then it's donkey work and you let the computer do it. You do it for all the depths, all the location, integrate over the time, and then you can have a map of primary production, or you can have a primary production at a particular location. And if you have measured primary production from in situ observations, this is the time to check your calculations. You see if you're doing it right, if you have assigned your parameters properly, and then you verify whether your model is able to reproduce the observations. So to repeat what I have said very quickly, these are the basic steps in computation of primary production. And if you are doing it in a remote sensing context, you can do steps 1, 2, 5, and 6 from satellite or in situ observations. But if you are in a satellite context, bear in mind that you would want to define the biomass profile and the parameters based on best estimates that you have from in situ observations. So the problem is that these parameters, especially the photosynthetic parameters, are not readily available everywhere at all times for you to do global primary production on a daily basis. So it's useful to break down the problem into two components. First one is to construct a local algorithm which you are satisfied, and then satisfy yourself that it works locally when you have all the information needed to drive your model. That means have all the parameters for your model. In large-scale calculations, then, you need to undertake one more step. You have to decide how we are going to extrapolate sparse local measurements to the global scale. What principles to use, what assumptions to make when you have a small number of observations and now you want to assign parameters at every location and at every point in time. So one of the methods that we have used in the past, and we still use it, is to use the concept of ecological provinces in the ocean, put forward by Longhurst in one seminal work. A couple of books have been published on it. And the idea is that we know that within ecological provinces, a given province, there is some homogeneity in the population of phytoplankton, in the forcing fields and how they are responding. So we have some justification in saying that the parameters may be assigned according to where these different provinces occur and what are the dynamics of photosynthetic properties in each of those provinces. So in the very first calculation that we did, we partitioned the information on photosynthetic parameters and chlorophyll profile parameters by season and by province, and then used that kind of method to map the parameters at the global scale and then carried out the calculations. So you can think of this kind of an assignment as a static assignment. And more recently, we have looked at how we might be able to assign parameters in a more dynamic fashion, accounting for how the oceans might be changing even within a province. So one approach that we have used is the so-called nearest neighbor method. And the assumption then is a little bit different. We create a database of all the parameters as a function and then assign them or what's the word? Associate each of those parameters with proxies of the ecosystem that you can detect from satellite. In this case, surface temperature and surface chlorophyll, and then also what's not shown here is the time or the season at which these measurements are made. So when you want to assign the parameter at a particular location, you go to your database and you see which is the nearest observation that you have, where you can match the temperature and chlorophyll in your satellite data with temperature and chlorophyll and season in your database. You look at the 10 nearest neighbors and then do some kind of an averaging and then assign the parameter to that location for that time. And you can do this for each of the parameters. It's a nice method, we think, but the problem is that you need a rich database that you can use to assign parameters. As Trevor said, his group spent years collecting hundreds and now thousands of data points for the Northwest Atlantic. So it's straightforward or easier to do it in the Northwest Atlantic than just about anywhere else in the ocean. So a few years ago, we tried another method, and that was to relate the photosynthetic responses to physiological models that say how they might change with light, nutrients, and temperature, and then use that as a basis for parameter assignment. But then if you want to do assignment based on nitrogen, that's not readily available from satellites. So we made a satellite analog of such models by saying that if you know how much chlorophyll is there, that's also telling us how much nitrogen had been available to produce that much nitrogen. So then biomass becomes a proxy for nitrogen supply, not necessarily concentration. And then we use that to map the parameters. I'm running out of time. So one way or another, if you can calculate primary production after assigning all the parameters, then you get results such as this, which can be used to analyze over time whether there are changes or not. This is one example of our calculation using province-based parameter assignment. And this is one example for 1 month in 2004. Tom, these data are still available publicly?
Yep.
Can you tell them sometime where you can get them if anybody is interested?
Yeah, I think it was in my talk actually.
Yesterday? Yeah. Sorry,
Yeah.
I missed that. I'm sorry. Okay. So you know where to find it if you want it. So maybe this is where I stop. And if you can bear with me, I want to make a couple of points. One is this. If you are thinking about how to compute primary production at the global scale, what does satellite observation bring to the problem? You can think about the problem in this way. You want to know primary production, and then you can express the primary production as a biomass or chlorophyll normalized production, and then you multiply that by the chlorophyll concentration. The advantage of doing it in that way is that this biomass normalized production is quite stable, because you are looking at, relatively speaking, you are looking at how production might vary if you always had the same amount of chlorophyll in the water, 1 unit of chlorophyll. Then that quantity only depends on how much light is available and how the parameters might vary. Then you have to multiply it by the chlorophyll concentration itself. And chlorophyll concentration has a huge dynamic range from about 0.01 to maybe 100. And that's the part that you can get from satellites. You might wonder what we are doing about the effect of temperature and nutrients. And these effects have to be accounted for in how you assign your parameters. Then there is the light effect, and that you account for by using the surface light and a light penetration model. So you can think of remote sensing of primary production as a method that makes use of all the in situ information on the parameters and then combines it with all the information at the global scale on the variables, that is chlorophyll and light, to compute the primary production at the global scale. So it's a method that combines in situ information with satellite observations to get the best estimate we can of total primary production at the global scale. I think I'm running out of time, so let me just mention this. Again, I want to mention that if you read the literature, you will find a variety of methods, models that say this is different and this is better. But regardless of which method and which model you are looking at, remember this. You need a basic set of 4 parameters to run your model. You need the initial slope of the photosynthesis irradiance curve. It may be called something else, but you need to know how light responds at low light, that linear response part. You want to know what is the assimilation number. You want to know how light production saturates when light increases. You want to know the specific absorption coefficient of phytoplankton, because that is an important component in all light penetration models. It affects how that attenuation coefficient K varies. So you want to know that. If you are using an absorbed light model, so-called, you want to know how much light is first absorbed before you calculate the primary production. And that also depends on this, will require the specific absorption. If you want to use a carbon-based model, and it's only for those models rather than chlorophyll, you need to know how to convert between carbon and chlorophyll. Given that the satellite gives you chlorophyll concentration, and there are some ways in which you can get it, or people say we can get at carbon, but bear in mind that satellite has no carbon signal that it can directly pick up. And if it does pick up a carbon signal, it's picking up the total carbon in particulate from the ocean. And you still need to find which component of that is phytoplankton carbon. So you're adding steps of complexity to your model. And at some point, you will need to know the relationship between carbon and chlorophyll. Of all these parameters, the carbon to chlorophyll ratio is the one that we know the least about. The photosynthesis irradiance parameters, initial slope and assimilation number, we have just more or less published a database on those, and there are about 5,000 or so data points in that database on a global scale. But if you want to look at carbon-based growth rates or carbon to chlorophyll ratio, I'm not aware of any such database. Most of the models so far rely on culture measurements. And if you're lucky, we have 20, 30, 40 observations from cultures. It's a big step to go from there to global calculations on in situ mixed populations. So in our group, we feel that this is another area of research. How can we best represent the carbon to chlorophyll ratio of phytoplankton? What confidence do we have in that estimation? Tom Jackson and us, we just published a paper on that particular problem. But it is, I don't think, a closed problem. And when we understand that better, how carbon to chlorophyll ratio varies, photoacclimation, and all those things, then we would be able to reconcile even better carbon-based models, chlorophyll-based models, absorption-based models, and so on. And that's just about where we are. And I'm sorry, I ran a little longer than I meant to. And I will stop here. Thank you.